Question 11. Which of the following relationships would most likely show a negative correlation? And a negative correlation is one where as one variable increases, let's say x, the dependent variable y decreases. And that can be seen here as a negative gradient in the line of best fit. Let's consider option A, the population of a town and the number of hospitals in that town. Generally speaking, the greater the population, the more hospitals one would expect to find. This would be an example of a positive correlation. So option A is out. Option B, the hours spent training for a race and the time taken to complete the race. Generally speaking, the more one trains, the better their time is going to be. And a better time means a lower time in a race. Now we're assuming it's a running race of sorts, or a race where against the clock or against someone else, for example, or against another group of people. The better time is a lower time. So that could be an answer. Let's have a look at option C, the price per litre of petrol and the number of people riding bicycles to work. So as more and more people ride bicycles to work, maybe the price of petrol might go up to compensate for the fact that there's less cars on the road. I don't know. But with option C, there's a lot of other factors that affect the price of petrol, not just the number of people riding bicycles to work. So while option C might look like a potential answer, it's not as appropriate as an answer as compared to, say, B, where it's a bit more explicit and direct that training for a race and the time taken to complete the race are more correlated, so to speak, than, say, option C, where there's so many other factors that affect the price of petrol. And option D, the number of pets per household and the number of computers per household, generally speaking, probably no relationship there at all. So option B would be the most appropriate answer. Question 2. Which graph best shows data with a correlation closest to 0.3? Now 0.3 implies a weak positive relationship. So option C is out, and option B is out as well, because they look like negative relationships or even a zero relationship in the case of option B. Option D looks like a strong positive relationship. So option D is out. In fact, if you were to draw a line of best fit by eye, you can see that the points are fairly close to the line. So that leaves us option A as the only solution. And in fact, if you were to draw a line of best fit by eye, we can see that the points are somewhat away from the line, but at the same time showing a positive relationship. So answers A. Question 28b. Ahmed collected data on the age A and height H of males aged 11 to 16 years. He created a scatter plot of the data and constructed a line of best fit to model the relationship between the age and height of males. Part 1. Determine the gradient of the line of best fit shown on the graph. Now to do that, we choose 2 points that are some distance apart from each other on the line itself. I'm going to use the 2 endpoints of the interval. So this point here has coordinates 11, 146, and this point here has coordinates 16, 176. Then we apply the 2-point formula to calculate the gradient of the line. So that's the formula, m equals y2 minus y1 over x2 minus x1. Now y2 and y1 correspond to the y coordinates of these 2 points, and x2 and x1 correspond to the x coordinates of the 2 points. And it's very important that we get the order correct as well. So this is x1, y1, this will be x2, y2. So back to the formula. So substituting in those values into the 2-point formula for gradient, we have 176 minus 146 over 16 minus 11, and that gives us a gradient of 6. Part 2. Explain the meaning of the gradient in the context of the data. Now we found in part 1 that the gradient equals 6. But what does that mean in the context of this situation? Now, the y-axis represents height, the x-axis represents years. So the gradient represents the change in height per year. So a typical response would be that the gradient represents the height gained per year, which in this case is 6 centimeters per year. Part 3. Determine the equation of the line of best fit shown on the graph. Now the line is in the form y equals mx plus c. That's the gradient intercept version of the line. So let's start off with that. Y equals m multiplied by x plus c. And we know that m equals 6, and we found that in part 1 earlier. So let's substitute m equals 6 into this equation. So now we have y equals 6 multiplied by x plus c. And we need to find c by substituting a known point on the line for x and y. So for example, I could use the point x equals 11, y equals 146, and that's this point here. And then solving for c. So y equals m multiplied by x, so substituting 146 for y, and 11 for x. We have 146 equals 6 multiplied by 11 plus c. 146 equals 66 plus c, since 6 times 11 equals 66. Then we subtract 66 from both sides, or just move this positive 66 from the right-hand side to the left-hand side. So it becomes 146 minus 66 equals c, and hence c equals 80. So that would correspond to the y-intercept. So therefore, y equals 6x plus 80. But to answer the question fully, we need to use the correct pronumerals. Y represents the height h, and x represents the age a. So h equals 6a plus 80. Part 4. Use the line of best fit to predict the height of a typical 17-year-old male. So we're going to use the equation that we found in part 3. H equals 6a plus 80. A represents the age of the male at 17 years of age. So we're going to substitute 17 for A. So H equals 6 multiplied by 17 plus 80. And of course, evaluating that, we get H equals 182 centimeters. Part 5. Why would this model not be useful for predicting the height of a typical 45-year-old male? There are a number of ways to answer this part. Here is my sample solution. The line of best fit is based on heights from ages 11 to 16. Extrapolation beyond those ages is inaccurate and unreliable. Hence, the model is invalid for predicting the height of a typical 45-year-old male. Question 30b. The scatter plot shows the relationship between expenditure per primary school student as a percentage of a country's gross domestic product, GDP, and the life expectancy in years for 15 countries. So part 1. For the given data, the correlation coefficient R is 0.83. What does this indicate about the relationship between expenditure per primary school student and life expectancy for the 15 countries? So this question is about interpreting this number, 0.83. Now it's fairly close to 1. So we can conclude that there is a strong positive relationship or a strong positive correlation between expenditure per primary school student and life expectancy. Or you could state that the greater the expenditure per primary school student, the greater the life expectancy. Part 2. For the data representing expenditure per primary school student, QL is 8.4 and QU is 22.5. What is the interquartile range? Now the interquartile range is given by the formula QU, or upper quartile, minus QL, or lower quartile, and that's 22.5 minus 8.4, given the information in the question, and that gives us an interquartile range of 14.1. Part 3. Another country has an expenditure per primary school student of 47.6% of its GDP. Would this country be an outlier for this set of data? Justify your answer with calculations. Now firstly, 47.6% appears significantly bigger than the upper quartile of 22.5%. So firstly, we need to determine what the outlier upper boundary is, and then check if 47.6% exceeds that upper boundary. So the outlier upper boundary is given by the formula upper quartile plus 1.5 multiplied by the interquartile range, and we found that in part 2. So substituting in the values for QU and IQR, we get 22.5 plus 1.5 multiplied by 14.1, and that gives us an outlier upper boundary of 43.65%. And clearly 47.6% exceeds 43.65%, so therefore 47.6% is an outlier. Part 4. The expenditures per primary school student for the 15 countries in the scatter plot are 5.9, 7, 7.6, all the way through to 27.6. Complete the table below by calculating the mean, x bar, and the standard deviation, sigma x, of these data. Calculate both values to 2 decimal places. The table also shows the mean, y bar, and the standard deviation, sigma y, of life expectancy for the same 15 countries. So calculating the mean and the standard deviation, we need to use the stat mode on the calculator. So press mode and choose stat. Now on this calculator, the FX100 AU plus, it's number 3. On the FX82 AU plus or plus 2, it's mode 2. Okay, so 1 var, and then just type in the data. So 5.9, 7, 7.6, so all the way through to 27.6. Okay. Press the AC key, then press Shift 1. Okay, I'm going to go to var, so number 4 here, and number 2, X bar, and we get 16.14. And for the standard deviation, sigma x, okay, so press number 3. And we get 7.02745, but rounding that to 2 decimal places, that's 7.03. And this is what we obtain. Part 5. Using the values from the table in part 4, show that the equation of the least squares line of best fit is y equals 1.29x plus 49.9. So here are the values from the table in part 4. And we also need the formulas for determining the gradient and the y-intercept of the least squares line of best fit. And they may be found in the formulae and data sheet under least squares line of best fit. So that's this formula here and this formula here. And I've just written them here as part of the solution. So we need to determine the gradient first, and then using the gradient, we can then determine the y-intercept. So the gradient equals 0.83, correlation coefficient, multiplied by 10.94 divided by 7.03 in brackets, or you can write it as a fraction. And we get 1.29, correct to 2 decimal places. And we can use this value to determine the y-intercept now. So using this formula here, that's 70.73 minus 1.29 multiplied by 16.14. And we get 49.9, correct to 1 decimal place. So therefore, the equation of the least squares line of best fit is y equals 1.29x plus 49.9 as required. Part 6. On the scatter plot on page 30, draw the least squares line of best fit, y equals 1.29x plus 49.9. Now to locate and draw a line, you need a minimum of 2 points. Now one of those points is the y-intercept 49.9. So that's given already. So to determine the coordinates of a second point, choose an appropriate value of x, substitute it into this equation, and then find the value of y that corresponds to that value of x. So I chose x equals 30, as the x coordinate of my second point. Substitute x equals 30 into this equation, and the y value that corresponds to the x value of 30 is 88.6. So plotting those 2 points on this grid, there's the y-intercept, 49.9, so it's approximately 50. And when x equals 30, y equals 88.6, so that's approximately here in this location. Joining those 2 points, we get the graph of the least squares line of best fit. Part 7. Using this line or otherwise, estimate the life expectancy in a country which has an expenditure per primary school student of 18% of its GDP. Now there's 2 ways we can answer this question. Using the line as stated, and we do that by locating 18 on the x-axis, projecting upwards until we strike the least squares line of best fit, and then projecting across to the y-axis, and we get a value that's fairly close to 74 years. The other way to work it out is using the algebra by substituting x equal 18 into the equation and then determining the value of y when x equals 18. So letting x equal 18, y equals 1.29 multiplied by 18 plus 49.9, and we get 73.12 years, or 73 years if you want to round it to the nearest whole number. Or if you use the line, it's 74 years from the graph. Part 8. Why is this line not useful for predicting life expectancy in a country which has expenditure per primary school student of 60% of its GDP? Now, to help you think about a response to this question, let's have a look at the least squares line of best fit that we drew earlier. So there's x equals 30% there. So 60% is way off to the right-hand side. And I guess the question is it safe to assume that this trend will continue forever and ever, or all the way up to 100%? And something else to think about is when x equals 60, calculating the life expectancy when x equals 60% gives us a life expectancy of 127.3 years. So clearly that does not sound reasonable. So the least squares line of best fit is based on x values from 5.9% to 27.6%. So that's what we've said before. It cannot be assumed though that the trend will continue in the same way beyond x equals 27.6%. So extrapolating beyond x equals 27.6% would therefore be invalid. Question 19. The table shows the life expectancy, expected remaining years of life for females at selected ages in the given periods of time. In 1975, a 45-year-old female used the information in the table to calculate the age to which she was expected to live. 20 years later, she calculated the age to which she was expected to live. What is the difference between the 2 ages she calculated? So in 1975, the age at which she was expected to live would be her current age, or the age in 1975, which is she was 45 years of age, and she was expected to live another 34 years. Okay, so 5 plus 4 is 9, 4 plus 3 is 7. Okay, so that's 79 years of age is the expected age which she's going to live to. 20 years later, so this is 1995, so using this row here, okay, she's 65 years of age by then, so adding another 20 years, and she's expected to live another 19.8 years. Okay, so that takes it almost to 85 years of age, so that'll be 84.8 years. Okay, and the difference will be, okay, so if you don't trust yourself, you can always just use your calculator. Make sure you don't make a mistake here. It'll be 5.8. Okay, so difference is 5.8 years. Option Question 28E. The shoe size and height of 10 students were recorded. Part 1. Complete the scatter plot and draw a line of fit by eye. So there's the scatter plot. And we might just have a look at part 2 and 3 quickly. We're going to use the line of fit to estimate the height difference between a student who wears a size 7.5 shoe and one who wears a size 9 shoe. And then part 3, a student calculated the correlation coefficient to be 1 for this set of data. Explain why this cannot be correct. In fact, part 3 could be in fact answered first. Just by looking at these points, we can clearly see that a correlation coefficient of 1 is a perfect correlation where all the points would lie on the line. But we need to draw the line first and just show it at least. So let's do part 1. Complete the scatter plot and draw a line of fit by eye. Okay, so we've got, okay, I might just zoom out for this. All right. 6, 7, 8, 9, we got 9.5. Thankfully, the tables in ascending order, so the shoe size, so 6, 7, 8, 9, 8.5, sorry, 9.5 is there. We've got 10, 10, 190, so that's another point. Okay, so there's one there. Okay, we've got 11 and 185. Okay, so that's about there. Okay, we have 12, 200, so that's another coordinate. So that's here. And finally, 12, 195. So 12, 195, so that's here. So it's possible to have the same x coordinate, but have two different y coordinates. And in fact, that happens here, shoe size of 7. Okay, that's 1 mark just for plotting a point. Now we need to draw a line of fit. It's not a line of, well, we try and make it the line of best fit. It's not going to be the best necessarily. So we draw a line such that half the points, I'll just zoom in again, so that half the points are above the line, half are below. And we also try to minimize the distance as much as possible from or between each point and the line. So I'm thinking this is where a clear ruler, in fact, is really handy. So there's no real, I guess there's no perfect answer. I think that probably would suffice there. They've got 4 above, 4 below, and I'd say that's probably, yeah, it's probably the most ideal one. In fact, I might even put it this way. Maybe between those 2 points, in fact. So I might just do that. Yep. Okay. I'll just rub that out there, so a little bit over. Okay. So that's that for 2 marks. Let's have a look at part 2. Use the line of fit to estimate the height difference between a student who wears a size 7.5 shoe and one who wears a size 9 shoe. So now we no longer use the points, we use the line. So a 7.5 shoe, so that's just here. Okay, so this is where we can project vertically from the x-axis. Okay, so that's about there. Okay, and across we have, that's 162. Okay, so that corresponds to 162 centimeters, and a student who wears a size 9 shoe. Okay, so that's easy enough there. We could just project to this point here. So once it strikes the line, we project across, and we get, well, it's roughly around 175. It doesn't have to be super exact, okay, as long as it's actually about 174. Okay, so size 9 corresponds to 174 centimeters. Okay, so 174 minus 162. Okay, and that's equal to 12 centimeters. That's the height difference. Okay, now let's get back to our part 3. A student calculated the correlation coefficient to be 1. Explain why this cannot be correct. Now we can clearly see why. Okay, you can see that the points do not lie on the line. Okay, so do not all lie on the line. So correlation is not perfect. Okay, probably have to leave it at this point. Okay, I've run out of space, but yeah, so points do not all lie on the line, so correlation is not perfect, therefore it can't be 1. Okay, and we'll leave it at that. Question 3. The graph shows a scatter plot for a set of data. Which of the following is the best approximation for the correlation coefficient of this set of data? Now, if we just draw a line that roughly represents the trend, okay, of the scatter plot, we can see it's a sort of a downhill, a negative gradient, which means a negative correlation coefficient. So it certainly can't be option C. It can't be option D since they're both positive. The dots or the points are fairly far apart, or reasonably far apart from the line. -1 implies a perfect correlation. In other words, all the dots lie on the line itself. So it certainly can't be A. -0.3 makes sense. This implies a weak negative correlation. Option B. Question 29D. 5 students sat both a physics and a chemistry exam. The results are shown in the table. The mean and standard deviation of each exam are also shown. The correlation coefficient for this data set is approximately 0.9. So part 1, verify the value of the correlation coefficient using your calculator and give your value correct to 3 decimal places. So we'll do just that. Put the calculator in stat mode. Okay, and A plus BX, not 1 var of course. And we should have 2 columns, X and Y. And let's just enter in the data as shown. So physics, that's top row there. So we'll enter that. So 75, 55, 81, 64, and 72. Okay. Now let's enter in the second row, chemistry. 84, 48, 77, 53, 68. Okay. Press AC. Let's invoke the stat menu and pick option 5, reg, for regression. Okay, and we'll pick option 3, so R for correlation coefficient. And we get 0.906807 ... Okay, but we need to round that to 3 decimal places. So that's going to be equal to 0.907. Now part 2, by using the appropriate formulae from the formula and data sheet and the given information, determine the equation of the least squares line of best fit. Now in the old syllabus or the previous syllabus, there were equations and formulae that you would need to use, but we can just use the calculator and get the calculator to determine the gradient and the Y-intercept, of course. So we'll just do that. Okay, you're welcome to use the formula sheet if you want to work it out the manual way. Okay, so shift 1, okay, reg 5, and we're going to use option 1 and option 2. So option 1 gives us the Y-intercept, which is negative 29.484. Okay. Next we need the gradient. Okay, option 5 reg and option 2 there, and we get 1.376. So therefore the equation of the least squares line of best fit is equal to 1.376x minus 29.484. 484. Question 29e. The graph shows the life expectancy of people born between 1900 and 2000. Part 1. According to the graph, what is the life expectancy of a person born in 1932? So let's find 1932 on the x-axis, okay, which is just there. Project upwards, we strike the line just there, and then project to the left until we strike the y-axis. So that's where we end up, and that's 68 years. So we have a 68-year life expectancy. And part 2, with reference to the value of the gradient, explain the meaning of the gradient in this context. So we need to find the gradient first, of course, and to find the gradient we just pick two convenient points, and we could in fact maybe choose this point here. Okay, so we might just circle that, and maybe this point here. I try and choose 2 points that are as far apart as possible, but ones where it's very clear what the coordinates are. So let's work out the coordinates for the first point here. So x is 1900, comma 60. And this point here, the x value is 1980. And the y value is 80. So let's use those two values then to calculate the gradient. So m is equal to rise over run, which is equal to y2 minus y1 over x2 minus x1, which is equal to, now y2 minus y1, that's 80 minus 60. Over x2 minus x1, so that's the run, 1980 minus 1900. Okay. And that's equal to, let's work this one out quickly, 80 minus 60 over 1980 minus 1900, and we get 1/4 or 1/4. Okay, so what does this value mean then in the context of this life expectancy graph? So this means that each year what's happening to the life expectancy? The life expectancy of people, as the years sort of go on, the life expectancy is getting higher by how much? By 1/4 of a year. Life expectancy increases by 1/4 of a year, or 1/4 of a year, or 3 months. Per year. Question 3. The graph shows the relationship between infant mortality rate, deaths per 1,000 live births, and life expectancy at birth in years for different countries. What is the life expectancy at birth in a country which has an infant mortality rate of 60? So what we do, we identify the infant mortality rate first, the axis that corresponds to that, which is the x-axis. We find where 60 is, which is here. What we do is get a ruler, okay, project up until it touches the line, and then we project across to the y-axis. Okay. And that value there looks like 68. Answer A. Question 12. Which of the data sets graphed below has the largest positive correlation coefficient value? So it certainly can't be A, because that's a correlation coefficient of 0, so that's gone. It can't be B, because that's a negative correlation coefficient. In fact, that's a correlation coefficient of 1, because the dots sit perfectly on the line. So this is R is in fact equal to -1, not 1. Let's have a look at D. Okay, there's a positive trend, but the dots are fairly, I guess relatively speaking, far away from the line, compared to, say, option C, where the dots seem to show a positive trend, but seem to sit closer to the line compared to option D. So it's most certainly option C. Question 29D. Data for life expectancy, expected remaining years of life for females at selected ages are given in the table. Now this question has been modified to make it more compliant with the current syllabus. You can just use the calculator now to come up with the least squares line of best fit, which is what we're going to do now in part 1. A student is finding the equation of the least squares line of best fit relating to life expectancy Y for females and their age X. So find the equation of the least squares line of best fit expressing the gradient and the Y-intercept correct to 2 decimal places. And this is where we use the stat mode on the calculator. So I'm going to run through this quickly. So we press mode 2 stat and we press this option 2, this A plus BX. And you should see 2 columns there. If there's a third column there, it doesn't really matter. It's the frequency column. We can in fact switch that off. We don't really need it. Shift setup, scroll down, and option 3 here, stat. And you can turn the frequency column off, number 2. So that's better. Let's enter in the data. So I enter it in column at a time. So 0, 5, 10, 15, 20, 25, 30, 35, 40. So we've got 9 pairs of data there, and just enter in that second column. So 84.6, 79.9, 74.9, 69.9, 65, 60.1, 55.1, 50.2, and 45.4. AC, shift 1, and you see this option come up here, reg, which means regression, number 5. Okay, and A represents the Y-intercept, B represents the gradient. Okay, so I'm going to write this now as Y years is equal to, I'm going to write it in the form Y equals mx plus c. So I'm going to press the 2 first, and the gradient is -0.98 times x plus or minus whatever the Y-intercept is going to be. So shift 1, reg number 5, and A for the Y-intercept, which is 84.69 or 84.70 to 2 decimal places. Part 2. A student uses the least squares line of best fit from part 1 to estimate the life expectancy of her grandmother who is currently aged 87. Explain why this does not give a valid estimate. So I think what we'll do, why don't we substitute in 87 into this equation and let's see what happens. So y equals -0.98 multiplied by 87 plus 84.70. Okay, so let's enter that in and see what we get. You'll probably get a very strange answer, in fact. Multiplied by 87 plus 84.70, negative 0.56. Which is a negative life expectancy. which makes no sense. Okay. Now, over the next page, because this question does go over 2 pages. So, part 3, Sally is a female, aged 37. Use the least squares line of best fit for females. That's y equals negative 0.984x plus 84.69. Okay, so we've sort of increased the number of decimal places there to calculate her life expectancy. So again, let's just substitute in the age, or her age, which is 37, negative 0.984 multiplied by 37 plus 84.69. Okay, so negative 0.984 multiplied by her age 37 plus 84.69 is equal to 48.282. I'm not going to round this one. It doesn't say to round it. I'm just going to leave it as is. So that's her life expectancy. Part 4. For males, the least squares line of best fit relating to life expectancy y and age x has the equation y equals negative 0.972x plus 80.44. Slightly different to this one there. James is a male. He marries Sally, who is aged 37. Okay, so take a hint. We're going to need to refer to part 3. On their wedding day, they have the same life expectancy. Calculate James's age on their wedding day, give your answer in years. So this is a case of we need to use Sally's life expectancy. James has the same life expectancy as well, but we're going to use a different equation, and we're going to solve for x. So let's do that. So we've got 48.282, since James and Sally have the same life expectancy, but we're going to use a different least squares line of best fit, is equal to negative 0.972. So that's this equation here. That's what we're told to use. X plus 80.44. And we need to rearrange this equation in order to solve for x. So let's do that. So we're going to subtract 80.44 from the left-hand side. So I'll show all the steps here. 282 minus 80.44 is equal to negative 0.972 multiplied by x. So if you want to, we can evaluate the left-hand side. You don't have to do it this way. This is just for you to have a look just at how this is all shaping. So that's negative 32.158 is equal to negative 0.972 multiplied by x. Now we're going to divide both sides by negative 0.972. Okay, so negative 32.158 divided by negative 0.972 is equal to x, since multiplication becomes division when we move this over to the other side. And hopefully we'll get a positive answer. So negative divided by negative, I'd expect to get a positive. Okay, so divided by negative 0.972, and we get 33.084. Okay, so James is around 33 years of age. Question 23. A set of bivariate data is collected by measuring the height and arm span of 7 children. The graph shows a scatter plot of these measurements. Part A. Calculate Pearson's correlation coefficient for the data, correct to 2 decimal places. Part B. Identify the direction and strength of the linear association between height and arm span. In Part C, the equation of the least squares regression line is shown. A child has an arm span of 143 centimeters. Calculate the predicted height for this child using the equation of the least squares regression line. So let's have a look at part A, which is to calculate Pearson's correlation coefficient for the data. So we'll turn the calculator on, put it into stat mode, so we'll press mode, number 2, stat, and because it's bivariate data, we're going to go to mode 2, okay, and you'll see the two columns X and Y, so let's enter in the data. Okay, so this first point here is 136 for X. Actually, it might be quicker if you just do all the X values first, and then we'll do all the Y values. Because every time you press equals, the cursor goes down on the calculator, it doesn't go across. So this one here is 140. Okay, this one is, there's 244s. 144. We have 146. And we have 148. Okay. Now let's scroll back up and let's do the Y values. So we have 142. We have another one that's 142. This one's 146. This one's 148. This one's 149. This one's 150. And this one is 152. Press AC. Okay. Now, bring up the statistics menu, Shift 1, and number 5, Reg. And option 3, R. We get 0.98. Now it says identify the direction and strength of the linear association. Now the correlation coefficient is positive and it's very close to 1. So this would be a positive and strong. Linear association. And you can see that actually from the dots on the scatter plot, that if you were to draw a line of best fit, the dots they align fairly close to the line. So you'd expect it to be, it's positive, and you'd expect it to be a strong, you know, wouldn't say probably moderate, but anyways. Part C, the equation of the least squares regression line is shown. So a child has an arm span of 143 centimeters. Calculate the predicted height. So this is just substitution. So height is equal to 0.866 multiplied by arm span, and arm span 143 plus 23.7. 0.866 multiplied by 143 plus 23.7, and we get 147.538. And we can round that to the nearest centimeter. So this will be 148 centimeters to the nearest centimeter. Question 12. For a set of bivariate data, Pearson's correlation coefficient is -1. Which graph could best represent this set of bivariate data? Now, it helps to know some of your correlation coefficients. Correlation coefficient of 0 means no correlation whatsoever, and it looks like a cloud of dots. But when there's a pattern there, if it's an upward trend, it's a positive number for the correlation coefficient. If it's a downward trend, then it's a negative number. So given that it's -1, and -1 is the absolute sort of least in terms of the number that it can be, and -1 implies a perfect negative correlation. In other words, all the points will lie on a straight line. And it looks like option D is the perfect candidate. And option D, it is. Now just quickly, option C would be a correlation coefficient of +1. Option B would probably be around probably 0.75, negative 0.75 actually, because it's downward. And A would probably be positive 0.75. So moderate to strong. Okay, so anyways, answer is D. Question 36. A cricket is an insect. The male cricket produces a chirping sound. A scientist wants to explore the relationship between the temperature in degrees Celsius and the number of cricket chirps heard in a 15-second time interval. Once a day for 20 days, the scientist collects data. Based on the 20 data points, the scientist provides the information below. A box plot of the temperature data is shown. There's your box plot. We have the mean temperature in the data set is 0.525 degrees Celsius below the median temperature in the data set. A total of 684 chirps was counted when collecting the 20 data points. The scientist fits a least squares regression line using the data, x, y, where x is the temperature in degrees Celsius and y is the number of chirps heard in a 15-second time interval. The equation of this line is y equals negative 10.6063 plus bx, where b is the slope of the regression line. The least squares regression line passes through the point x bar, y bar, where x bar is the sample mean of the temperature data and y bar is the sample mean of the chirp data. So this continues on the next page. Calculate the number of chirps expected in a 15-second interval when the temperature is 19 degrees Celsius and give your answer correct to the nearest whole number. There's a lot going on in this question. So let's work backwards. We want to work out or calculate the number of chirps expected in a 15-second time interval when the temperature is 19 degrees Celsius. Going back to our equation of the regression line, it hinges on this. We need to find the value of B, or the gradient of the line. Now, working backwards even further, in order to get or to calculate B, we need x bar and y bar. Now, x bar is the average temperature. Let's go to the box and whisker plot. One of the points here is, or the second point is, that the mean temperature in the data set is 0.525 degrees Celsius below the median temperature in the data set. So let's see what the median temperature is then. It's 22. So it's important that you understand how to read a box and whisker plot and know where the median is. So let's start off. So what I'm going to do is I'm going to write down that the median temperature is equal to 22 degrees Celsius. Now the mean temperature is 0.525 degrees Celsius below that. So let's write that down. So the mean temperature, which is equal to x bar, is equal to 22 degrees minus 0.525. Okay. And we get 21.475. So this is x bar that we will need to use in order to be able to calculate the slope of the regression line B. Okay, now the next thing we need to work out is y bar. And that's the average of the chirps, okay, or the sample mean of the chirp data, okay, in a 15-second interval. And the third point, so let's make sure we get the points, the number of points correct, first, second, third point. The third point will give us y bar. Okay, we have 684 chirps was counted when collecting the 20 data points. So let's work out the mean chirp data. Well, it's the mean number of chirps actually in a 15-second interval. And that's in fact equal to y bar, which is equal to 684 divided by 20. Okay, so 684 divided by 20, and we get 34.2. Now, let's go to our regression line, okay, or the equation of the regression line. We know, and we're actually told, that the regression line passes through this particular point, x bar, y bar. Okay, so the regression line okay, I'll just write the equation again, just makes it easier. So it's y equals negative 10.6063 plus bx passes through the point 21.475, that's our x bar, and y bar is 34.2. Now we need to substitute this coordinate or this point into the regression line equation. So 34.2 is equal to negative 10.6063 plus b times x, or x bar, which is 21.475. Okay, so rearranging that equation, okay, we have 34.2, we're going to add on 10.6063. I'm going to put that in brackets. I'm going to do this all in one step. And then we're going to divide by 21.475. So this is just a little bit of algebra. 21.475. Okay, that's equal to our gradient. So therefore, b is equal to, okay, let's work that out now. So 34.2 plus 10.6063. Divide that by 21.475, and we get 2.086. I might just write the whole answer there rather than rounding it too early. 0.86440047. Now that we have the gradient of the line, we can now use this to, in fact, answer the question. So we want to work out how many, or calculate the number of chirps in a 15-second interval when their temperature is 19 degrees. So now, at x equals 19, okay, we have y is equal to negative 10.6063 plus 2.086440047 multiplied by x, which is 19. Okay. So working that out, we have negative 10.6063. Now, the value for b is in the answer memory, so I'm just going to use that. So just be very careful using that to make sure that that's in fact the correct value that you have in there, as long as you haven't done any other calculation. Times 19, and we have 29.036. Now to correct to the nearest whole number, we have 29 chirps. Thank you for watching.